Good afternoon, everyone. I welcome all of you to the 13th session of online faculty development program on AI in cloud computing, theory, practice, and applications. Now, the session will be handled by Dr. Yashwant Singh Patel. Let me introduce him to you. Dr. Yashwant Singh Patel is currently a postdoctoral fellow in the Department of Computer Science, Umea University, Sweden. He is also associated with the Computer Science and Engineering Department CSED at Thapar Institute of Engineering and Technology, Punjab, India. He received his PhD degree in Computer Science and Engineering from the Indian Institute of Technology, Patna in May 2021. He has authored more than 40 peer-reviewed papers and articles in high-impact journals and internationally reputed conferences, as well as one textbook on cloud and distributed computing algorithms and systems, published by Valley. His research interests include cloud edge systems, edge intelligence, serverless computing, energy-efficient computing, and distributed algorithms. We welcome you, sir. Now you can start
Okay.
the session, sir.
Okay. Thank you very much. Thanks for the introduction. Just want to check my slides are visible.
Yes, sir.
Okay. So hello everyone, and first of all, I would like to extend my gratitude to the organizers, Professor Sanjay and their team, for giving me the opportunity to interact with all of you. And since my introduction has already been provided, let's proceed with the discussion. This session is on AI-driven workload forecasting trends for cloud edge computing. And the theme of the workshop is very much related to what we are doing here in our advanced distributed systems lab, and that is much on a bigger scale. So I will start from some of the basics to make sure we are on the same page, and then I want to make sure you understand and take the necessary basics from here. And I will be starting from the cloud systems, the continuum modeling, and what are the key challenges while integrating different components, and what is the role of AI predictive modeling here in the cloud edge system use cases. And then we proceed with the deep learning based univariate and multivariate time series forecasting. What are the benefits of it? And then we'll focus more on how we can utilize this AI predictive modeling in cloud edge system. And then we look at some case studies with applying different kinds of advanced models, the stack models, hybrid models, and some other advanced deep learning frameworks for workload forecasting in cloud-based systems. Okay, so there's a very quick question like, where edge computing meets AI is closer to data sources. So I put a query. It says that a robot is standing on the edge with fog and cloud on the horizon over Chicago city. Now what you can imagine, what kind of image will be generated by these chatbots. So if I insert this query, I asked to ChatGPT or some other chatbot, let's generate some image on this. So what could be the possible use case? Any suggestion, any idea? So we have to generate an image, AI generated image, and it's asked like a robot is standing on the edge with fog and cloud on the horizon over Chicago city. Any guess from the audience, like what could be the possible image? Any answers? Will it be like exact depiction of these edge, fog, and cloud computing concepts, or uh, it will be something else? Okay, am I audible?
Yes, sir.
Okay, that's great. Okay, so this is an answer. Like you can see in this image, like a robot is standing at the corner in the edge, and is holding some data. And then you can see that in between we have kind of a foggy environment, and then at upward we have a cloud based atmosphere. So here you can see in this image, like a robot is holding some kind of cubes. These cubes are basically edited in the later phase with the AI editor. So this is we call as the data, and the robot where it's standing we call it as a edge, and in between these two, like in between cloud and edge, we have fog. So this is how we can generate an image. So this image was generated in IEEE services symposium, and it was a popular depiction of edge, fog, and cloud. So let us discuss with some of the examples. So first of all, what is edge computing? So edge computing is, as you can see in this image, is all about processing data in a geographically closer locations before sending it back to some centralized locations cloud. And if you take some example and understand like where this term the fog computing is coming. So uh, the story is all started with the content delivery network, and the term edge computing, it was started being used around the same time when the CDN was quite a lot in discussion, and the things get evolved more than that, and then the term edge computing is came into discussion. So this is a kind of a separate term from edge networking. So edge computing is now more associated with the kind of a IoT devices, literally like we have smartphones, cameras, sensors, household appliances, and vehicles, all thing in IoT. And since all of these things they gather data, and they are expected to do something fun and something exciting, they all need to either process information locally, like here a robot is holding the data, and or we can send the information they capture to a server, something which is in the remote cloud, and that does some processing and then acts based on what it has computed. So with all of these things out there, you could imagine that some of them need to react very quickly or possibly process the data that shouldn't be passed across the internet to a centralized server. And to add to that, the centralized server is could be like probably geographically far away from these things, which adds additional problems with that while quickly powered. So this edge computing solves these issues, and the way it's solved is by processing data somewhere other than a far away server somewhere in the cloud. So is all about the computation and the processing near to the data source. So let us check some real life example. So is a couple of real life examples are there, and this is Chick-fil-A Tech. You might have heard about it, or I guess not. So it's a popular fast food place for ordering chicken burgers. So no matter what you think of their politics, it is some kind of a sweet networking and edge computing studies going on. And if you don't know about it, then you can follow this link. Which is available on Medium. And what's the interesting thing about this? Like, how does it related to more with the edge computing? So basically, what they are trying to do, they're managing like 2,800 edge Kubernetes clusters, and Chick-fil runs a fleet of edge Kubernetes clusters in each of their restaurants, which is more than 2,000. And they have built and shipped a very mini Kubernetes clusters to each of their restaurants locations, and they allow for like local compute to happen at the store, and then they call back to home with the details. So this is an excellent example of edge computing at its best. So they also manage like hundreds of thousands of IoT devices, such as for fryers, for grills, or tablets, some kind of a user interfaces, and they send billions of messages in each month. So they have presented this demo in long back around like 2018 when the KubeCon consortium was going on, and uh, they basically built a restaurant chain that has a capacity to serve people, and you have to do it as fast as you can. So they serve like they prepare like one sandwich in every 16 seconds. So their IT team has collected the information like how many customers are there and how many equipments we have to run. And then for these 2000 restaurants, they have like hundreds of thousands of IoT devices. And they use like different kinds of IoT sensors to deliver it. So as you can observe, like here, they are placing all the data in their restaurant locations. They are not offloading anything. They are just sharing the higher level business and operation informations to the cloud. So this is one example of an excellent example of Kubernetes cluster. And second is quite popular. You might have seen it's connected cars. So I don't think that most people really consider it. But your car is probably edge compute node all on its own. And there are lots of advancements are going on, like Tesla. They have absolute ton of data is processed right inside the vehicle, and which includes like all the advanced safety and convenience features that use like cameras and sensors all over the car. And if you realize like most of the data that never leaves the vehicle, and instead of instead it's all computed right there at the edge with only the filtered or distilled data that is being sent to the mothership or the house. So this is one another example. And this is the quite popular picture of three-tier architecture of cloud, edge, and fog computing. And so what we have seen, we have seen a couple of example of edge computing. So what is fog computing? And to be completely honest, this is a kind of like splitting your hairs, and it feels like another buzzword which could generate some revenues. And another addition, the tech term glossary. So here you can see a three-tier architecture, and at the bottom we have edge layer. We call it like single board computers or some Raspberry Pi. And then we have a cloud data center at the upper layer, and in between we have this fog node. So fog computing, very simply if we discuss, it's somewhere between edge computing and traditional cloud data centers. And the best example which I could give, like let's consider a company network with a bunch of different sensors like motion sensors, smart light monitoring sensors, etc. And all of these devices may not provide much computing themselves, and even trying them together at the edge might be too close to get that big picture. And by taking one step out and bringing the data together on the network, but not far is the data center, you can get some valuable data, and then you can make some informative decisions without consuming the general internet bandwidth. So it exists somewhere between edge and cloud. And another popular term nowadays is called edge networking. And this is another common place where you hear the word edge come into play. Is this is we call edge networking. And this term, like it's generally applies the same concept, but it is slightly different from. Let's have a pointer here. Okay, so this is slightly different, and it basically related to more with content delivery networks, CDNs, and that will physically distribute like caching servers around the globe. Like we can have area 1, area 2, 3, 4, 5, the separate, the different locations around the globe. And with edge networking, when you make a request, for example, to uh, what this Google Meeting video is doing, so you are probably not getting the video served to you from the original source. It's way more likely you are getting served a cache copy of the video from a cache server at the network edge. So this feed is not on real time. Maybe you are getting a cache copy of this video. So this is all about like the story of CDNs or the edge networking. Okay, so over the last few years, this edge networking has gotten more and more advanced, and there are services like Cloudflare, and they now offer way more than just caching at their edge. They have something which is more advanced. They basically provide the controlling of IT and security across the on-premises clusters, the public cloud environment, software as a service environment, and the internet. And then they have like improved level of security. And they are now more advanced nowadays, and they offer new services with some configurations. They have the ability to distribute parts of website logic out to the edge as well. And this these kinds of services, like they have bot managed services, connectivity cloud, CDN, uh, something related to DDoS attacks and mitigation. You can find plenty of resources on this Cloudflare. And this takes the strain off from your pool servers that in the past would have to serve all of the dynamic content on its own. So this is another example of these kinds of services. And Versal is a quite popular. So this is another edge provider that many web developers who are very familiar with it, they are might having this, they might have heard about it. And it's a front end cloud which basically used for building, scaling, and securing and protecting our vaster personalized web applications. So with Versal, you can take an application and which is written with some popular kind of a meta framework, let's say Next.js, and you distribute to its edge network to make your website like highly available, more robust, and distributed with very little extra work. So whenever the term edge computing comes here, so just think about something which is distributed. And it says that is it like just a hype? Well, I said like yes or no, because this is certainly a real and useful tech. And if you lump it all together and forget all kinds of hyped devices, then you can find it, uh, which is something like moving closer to the data sources. Okay, so uh, this is just an optimal way to
Sir,
a
your voice is
great
breaking.
experience for the end user. And this is just mean like the distributed kind of stuff. And the basic slope says that slides, is it visible to you all?
Yes, sir.
Okay. Okay, so basically we are moving the compute power closer to the user. That is all about edge computing. And okay, I think this is some problem. Okay, and this is a very like this is an important term if you
Sir, not audible.
uh, want to learn about something about networking. So can you imagine a world where okay, am I
Yes.
audible now? Okay, good to go. So, like without telecommunication network, we can't imagine a world. Uh,
Sir, again some problem is coming, sir. It's not audible, clear.
the world is something. Okay, so the RAN is the radio access network. You can see here, and
Sir, voice is breaking, sir.
uh, the these RAN is
Sir, not audible, sir.
okay. I think it's disconnected again. Let me share. Okay. Am I audible?
Yes, sir.
There may be some network issue. And okay, so let's move towards the cloud edge continuum. And okay, so the infrastructures which we called as the cloud infrastructures, they are rapidly evolving from their centralized systems to geographically distributed federation of devices. So what we know about the cloud data centers, like there could be like distributed. They're geographically distributed in different locations. So if you take this Singh case study in example, so there could be a data center, like some data centers are in Norway, some data centers are located in Sweden, and uh, apart from the data centers, we have those IoT devices which are rapidly increasing nowadays, and it is estimated like the 50 billion connected devices by 2025. But there's another recent case study which says that there are more than 75 billion IoT devices will be deployed by 2030. And you can imagine like how massively this communication is growing. And the size of continuum is growing at an enormous rate. If you see in this picture, apart from these data centers, we have the distributed federation of edge devices. Uh, you can call it fog nodes or edge devices. They all are interconnected, and these blue ones, these are nothing but the your IoT devices. So there are lots of communications and computation stuffs are going on. So there's a complex federation of devices, and now this is an actual picture of what we think about the cloud and age. So instead of discussing about the three-tier architecture, where at bottom layer you have IoT and middle you have fog and upper layer you have a cloud, think something about the geographically dispersed volume or massively scale systems. And now, in this kinds of case study, the important and the critical point is like you have to balance load on the regional and the national power grids. So you have to ensure about the regional considerations, because there are a lot more discussion which is on uh, following or having the data sovereignty, the data policies, the energy policies. So, for example, if this region, this green region, this R1, if it wants to offload something from this location to another location, let's say this yellow one, then it has to adhere with all kinds of data policies which region this region is following. So you have to consider all kind of regional stuffs here. And apart from that, like we are in the research, we discuss more about the view on latencies, the data privacies. We ensure like we can serve maximum request, we can optimize the delay and revenue trade-off. But here the energy is quite evolving as more critical constraint, and you have to follow these energy considerations. So there are different characteristics of continuum because of the heterogeneity of devices, the infrastructure dynamicity is there. You have to ensure different kinds of privacy levels, and also we have massively complex federations which spread across the regions. So there are multiple geographically distributed providers, and each with their own policies, their own considerations, their own data processing capabilities. And we have the heterogeneity in the platform, because there are a lot more different architectures and different systems they are integrated. So they could be like different service providers like Vodafone, AT&T, China Mobile, telecom providers. There are different telecom providers are involved. So there will be platform heterogeneity. And also like Resource constraint devices, this is really important stuff. Some may process your data, some may not, because there are foundation with their computational capabilities. And the dynamic, yeah, the dynamic infrastructure is quite important, where we can automatically provision and adjust itself as a workload demand changes. And in cloud, we talk a lot more about the auto scaling. So based on the overloading and underloading of servers, which we call as a physical machine, we can offload or some of the load to other nodes or even to some other places. So there is a need of autonomic resource management or automatic resource management. And there is need of secure orchestrations over public network. So secure orchestration means it uses multiple what we call the automated tasks, which we can execute a complete and complex process or workflows. And if you consider this complexity, so this massive complexity results in consuming high amount of energy. So this will be like high energy consumption. Right? How much high it will be? So this is a very popular graph with respect to data center and network energy consumption. So it is estimated that this is a very popular study in the Gartner forum. So they estimated like data centers as a whole, they are predicted to consume as much as like 8% of global electricity supply. And apart from the global electricity supply, by 2030, it is also estimated that if we include the networks, then they can consume up to 18% of global electricity or electrical power by 2030. And also like in few of the recent articles, it is also said like the daily energy consumption of cloud data centers and edge networks is equivalent to the energy released by the Hiroshima atomic bombs. It is like more than 70 atomic bombs. So this is a figure which is constantly rising. So if you include these two things, the data centers, which is colored by this green region, and then we have this bluish one, networks, then it is something like near to 18% of global electrical power. So we are basically trying to aim for a bustling or the crowded smart city, where you can see like different traffic lights they adopt on the fly to different traffic flows, the energy grids. You can see the spikes in the demand, the uses levels, and the telecom networks, which they are different providers. They have to ensure like user behavior is fine tuned with their available bandwidth, the network bandwidth. And to make this vision a reality, we have to ensure we have to provide the precise forecasting for these factors. However, this challenge is immense, and as the dynamic nature of cloud and edge networks, we need a fine-tuned balance between demand and the available resources. And any misalignment, uh, such as like insufficient or excessive provisioning, it can directly impact the quality of service and also the operational cost. Now, in recent days, the buzz term, another buzz term is evolving, like the serverless computing. To manage this complexity, uh, the developer has suggested they go for like serverless computing. And for most of the developers, these architectures they generally offer like greater scalability, more flexibility, and quicker time to release, and all that at a reduced cost. And with the serverless architecture, developers they do not need to worry about the purchasing, provisioning, scaling, and managing the services. So without managing anything with the backend servers, they can simply scale uh, their they scale their services, and also it provides a lot of flexibility. So, what exactly is serverless? So, it allows the developers to put all their focus into writing the best front-end applications and the business logic, whatever they want, and they do not need to worry about the backend provisioning. And developers just write the application code and they deploy these into some kind of containers, and the cloud provider which is there, it basically handles all kinds of provisioning which is required to run the code and scale the infrastructures up and down on the demand whenever is needed. And the provider, they are basically responsible for automate the whole process, automatic provisioning, deploying and scaling the services based on different range of criteria. And also, like, there's one more important point. You might have heard about performance per watt or ppw. So in cloud data centers, we much more concerned about the power consumption of the idle servers. So with serverless, developers, they never pay for the idle capacity, so they have to pay as much as they are actually using in reality. So the provider, they spin up and provisions the required capacity resources based on the demand, and when the code executes and spins them back down again, that we call like scaling to zero. So execution is not stopped. You do not much more focus about the idle capacity of the resources, and the billing starts. The actual billing starts when the execution starts and when the execution stops. So the pricing model is much more on the execution time and the resources required. So that's why, like, nowadays much more research is going on with the serverless computing. How do we integrate? How do we go ahead with the monolithic architecture to this microservices based architecture? And it basically abstracting infrastructure away from the applications. So how does this work in a continuum environment given the characteristics discussed? So there are different kinds of research challenges when you talk about serverless computing at the edge. So we have different cloud edge systems. So we need a cognitive cloud edge management because we have multiple disaggregated and highly distributed architectures, and we have to deploy and perform the migration of the functions. They need seamless user access and programming models. We have to automatically offload the resources with the specific requirements. So when you are offloading a functions, you have to much more careful about their replicas of the functions which is deployed in the current region. So the offloading is not that much easy, but it provides like a seamless accessibility across the continuum. And as we talked earlier, like, there are multiple reasons are involved. So we need a like secure and trusted execution, because when you have the multi provider networks, you have to ensure the granularity of functions, which is have to provide a fine grained control. And there are new serverless functionalities, like how much execution is needed, like is it a short term execution and the long term execution. Also about you have to be careful about the location, so location awareness is needed. And the energy efficiency, and the adaptations to like green energy, the placements of task placement of function, but while ensuring the availability of green energy, how much green energy is available, how much will be required, what kind of modeling models we have. So to manage all of these challenges, here comes the role of AI models. So basically, the AI models and optimization techniques, they basically need to like how accurately they can manage and predict something without uh, having excessive latency and or overhead. Because we have seen like most of the predictive modeling in cloud data centers. So if you talk about the techniques like proactive and reactive techniques, so reactive is much more about the real time resource allocation. You are not worried about what will be happen in the future. You are taking a decision based on the current resource utilization. And you have to be a proactive, you have to adopt a proactive approach. So proactive approach is much more focused about you are planning something like how much resources will be consumed in the upcoming time steps or upcoming time intervals. So you are doing a planning, you are estimating something, and then you are preparing your infrastructure based on the upcoming request. So here comes the role of the AI models and the optimization techniques. And there's much more bigger term which we called AI predictive modeling. So AI is much like it uses the machine learning and deep learning to analyze past and the current data to predict future outcomes. And there's a popular meme which says that like machine learning is and deep learning, they are nothing but it is just glorified statistics. And but it is more than that. And with the predictive modeling, you start with collecting the data, after which you analyze the data, and then you build a predictive model that is used to generate some likely outcomes. There are a couple of examples like which is widely used in different range of instances and industries. For example, the insurance companies, they can predict with which additional policies a customer might be interested in purchasing in future. The hotels, they can find out which holiday dates they are likely to be overbooked. And the banks, the banks can predict which transactions are likely to be fraudulent and so much more. So similar to this, the predictive modeling is required. So it is not a one-time event, and the models, they must be constantly updating with the new data to ensure more robustness and more accuracy. And when you add new information and the adopting and dynamically changing external condition, so you are trying to make your old forecast much more robust. You are adding more data, you are trying to make your model more intelligent, and this is how you can improve your forecasting results. So there are different kinds of type of predictive models. So this is not much in detail, like you might have studied in different kinds of machine learning and deep learning algorithms. So broadly, we can say that this predictive analytics, it's much more classified today. We can call as a classification model, where you used to predict between two outcomes like true or false, yes or no, and something with like if you take the example of a traffic, so high traffic, medium traffic, or low traffic, something like which terms which is having some labels or the classes. And the forecast model, it is much more on the regression part. And this concerns like the numerical forecast, like you are predicting some value. For example, it can help an office supply store predict the number of backpacks to stock before a new school session starts. And also like uh, we are you are actually predicting like what will be the value of the workload. So basically you're saying that how much workload will be coming. So you are using this regression based model. The third one is like the clustering model. So clustering means you are categorizing the data based on their behavior, based on their factors into different groups, and without any prior classified labels or knowledge. Based on their characteristics, based on their inputs, you are labeling them. And the time series model. So this predictive model is very much needed nowadays, because you're continuously analyzing the time windows, and based on the time windows you are predicting some future events. For example, we can involve like analyzing the sales of a particular product. What are the sales of a product in the last 3 months, and based on that you're predicting the sales for the next 3 months. And this is much more evolved. Like if you are continuously monitoring your system, let's say for last 10 hours you have monitored, and you are predicting that what workload will be coming in the next 10 hours. So here the time series forecasting or time series models are useful. um, so basically, what is the time series forecasting? So it is basically the process of using the past workload traces, the historical data, and you make some prediction about the future events. And these time series data, it refers to like data that is collected over time, and which is typically used to model and forecast trends, patterns, and behavior. The machine learning accuracy in forecasting is crucial for handling complexities. It is basically a key to optimize resource allocation and ensure the high service quality. And if you talk about like edge computing models, so in edge computing, the models with low inference times are valued for quick decision making, and the optimal performance on resource constraint devices, and something more which is much more related to energy efficiency. And there are different kinds of applications of these time series forecasting, which is on finance, economics, marketing, engineering, and more than that. Like in sales, you can predict the future trends, what will the stock prices, the pattern of weathers, and the variables which basically change over time. So this is where the time series forecasting is involved. Okay, so yeah, these are some more examples. You know much more about it. Like we can predict the, you can take like the months, and you can predict like how much temperature will be there. And similar to that, like you can have a carbon emissions. Now, uh, this is like a much more concerned way, and I will share here like this is we can discuss more. Okay, I'm just switching it. Okay, is it visible? Okay, well, I hope it is. So, here, basically, this is one popular case study. So, this is for like those who are basically working with the carbon emissions and the carbon pricing or energy consumption effect. So what usually happen, like we have different kinds of renewable energy sources that are available. So for example, if you open this app electricitymaps.com, and if you search any area, let's say I want to know about what is going on in Germany, so you can see here like what is the electricity production sources. Like here you can analyze, you can see like there are different kinds of nuclear, geothermal, the biomass, wind, solar, different kinds of energy sources are available. And if you see the carbon emissions, you can check here like current carbon intensity, and how much renewables are available, and what are the energy sources. So here we have a chart which is based on different time horizon, and based on that you have the hourly carbon emissions. And this could vary with the reflected to different zones. Like in Sweden, the carbon intensity is much lesser, it is like 37 only. Here in Poland, the carbon intensity is much more higher. So it can give you like the estimation about this, and you can use this data to predict like what will be the carbon emission in the next couple of days or in the next couple of hours. So I will switch back again. Okay. Um, so uh, in the earlier example, we have seen like daily carbon emission. So this is one case study where we have carbon emission on y-axis, and on x-axis we have these different dates. So we can observe like what is the carbon emission on daily basis, and also with hourly we can measure it. And so we need something which we call autocorrelation. So autocorrelation means any quantity which is correlating to itself, that is we call as a correlation. And it estimate like what kind of growth rate or the energy consumption of country. It could be like increasing and decreasing trend. Now this is very this is not very difficult study. It's similar to like if you're predicting some arrival of passengers for a particular airline, you can estimate like based on the uh, past days, you can say that how many passengers are going to arrive in the next couple of hours. So you can find out the trends. So for this, like there are some very basic steps for forecasting, and you define your problem first, like what kind of model you want to create. So you have to focus more on what kind of problem you are trying to solve. It could be like inventory management, it could be like demand forecasting, weather forecasting, or capacity management. And then you can go ahead, and based on that you can collect the data, what kind of data is needed to solve the problem. And then we need to analyze the data, or you require some more data to solve the problem. And then once you have analyzed it, you build and evaluate the forecasting model, and you keep on checking its performance. So there are basically three thumb rule. One is called the granularity rule, frequency rule, and the horizon rule. So what is the granularity rule? So for example, let's look at this picture. We have years, and these are basically the number of subscribers with respect to years. So granularity rule, it says that, let's say Netflix is going to launch a new program for whole city or for whole state, and they want to predict like how much views in a month or next quarter will be coming. So there will be like lots of fluctuations, and noise will come. For example, in some region, in some places, people may like the show, or in some areas they may not be interested to watch the show. So if I go to like city level, then I may see a lot of better forecasting result. So if there's some Indian comedy show is going on, and if you're using Netflix in India, then there could be like more views. The number of subscribers will be more who are basically interested in that particular channel. But the same show which is telecasted or broadcasted on some other reason, and if it is an Indian show that people may not have that much of interest. So this is we call the granularity level. And these are the fluctuations are exist in this study. Another thumb rule is called the frequency rule, and this says like frequently, like I need to gather the data. Right, suppose which I need to need the predictor, the forecaster in the stock market needs. So we can regularly analyze, we can analyze the data at the regular interval. Like how should I get the data? And once you have get the data, you from the source, you can check like uh, what will be like the stock price in the next couple of days. So this is we which we call like more about the frequency. You're getting the data from the sources, and you are checking on its frequency. It could be high, maybe you have very less time intervals, and you have like uh, abundant of data. So the you can find out the frequency of that. And the third one is like the horizon rule. So horizon means suppose I have to forecast like for 3 years, uh, that may be like so high numbers. So in such a places where we decide the horizon, we should make sure that like if it is a short horizon, that will be more precisely predicted, which will be more accurate than the long horizon. So this is we call like the time window. Like what will be the time window for forecasting? So there are three components for the time series forecasting. One is called trend, seasonality, and noise, and the fourth one, which we call the level, which is nothing but the baseline. So what exactly is the level? So level is basically the actual uh, average baseline which we set for any time series data. And you can say like this is my level in a regression problem. So this is we call the level. And the trend is like you are analyzing your time series, and you say that this is going, let's say if stock prices, the trend of stock prices are going upward or it is going downward, and how the sales or inventory is going, okay, based on the historical trend. And there comes like the third one, which is like the seasonality. So you could have like seasons means the short term cycles in the series. For example, like in the December month, this is going to be the holiday time, and more and more sales happens of any product right there in these months. Or you could have a summer time where you have like holidays for schools and colleges, and you can say that this is the month where the sales is going high. So this is something like the holiday time. Or maybe the views which happens on any program or any OTT channels like Netflix or Amazon Prime. If you are on the weekend, you can say that okay, in this weekend, like in Saturday or Sunday, you can have spikes of the views, which is much more higher in compared with the weekdays, the weekdays. And you can say that weekend views are much more higher in comparison with the weekdays views. So this is we call the season. And there comes a noise. So noise is something like which is quite popular. So this like outlier, the random variation in the series, in these series. So there could be like outlier errors or noise. And based on these trained seasonality and noise, you can create a model. Like it could be an additive model, it could be a multiplicative model. So it depends on like the problem which you are creating. So if you're solving any problem, then you need more mathematical ways by incorporating the level, the average value of the series, the trend, the increasing and decreasing value in the series, the seasons, the short-term cycles where you see the what are the season, uh, and then you have some noise. Like here you can see these outliers in this image. Now, based on that, like we have different kinds of methods, and these methods are used for time series forecasting. And we have like you might have heard about the univariate time series forecasting, the multivariate time series forecasting. So it says like univariate, and you have like this is something like which is much more on the single dependent variable. And based on this study of dependent variable, you are finding the behavior of the other independent variable. So the basic assumption behind this univariate prediction approach is that the value of a time series at time step t is closely related to the values at the previous time steps like t minus 1, t minus 2, t minus 3, and so on. And for example, if you want to predict the CPU uses of a workload which is coming to any systems or any data center, then you predict the CPU behavior, CPU uses time steps of the data, and you say that okay, based on these CPU past CPU uses intervals, next time interval we will be having this much uses. So that we call the univariate. So where you have like one variable and then you are predicting for something for the target variable. And uh, like in the stock market, like forecasting is usually like what will the closing or opening prices. So you're using only one variable, what will the closing and opening prices based on the past few weeks data. And there comes like another one which we call like multivariate time series forecasting. So multivariate is much more involved where multiple variables are there. So you're fixing one variable, that is time, and others are like multiple parameters. Now, for example, you are predicting the CPU uses, but that CPU uses is based on the other. other parameters, like it could be based on the memory uses, the disk uses, the bandwidth utilization. So much more features are involved. And simply, if we take the stock market study, the multivariate stock market, so we are not considering only the relationship to the closing price, but also the moving averages, the highs and lows in the prices, and the other the stock parameters. And based on that, you are saying that tomorrow's the trend of stock prices, will it be higher or will it be lower? So using much more information. So these multivariate forecasting models, they are much more popular because uh, this somehow trying to provide you much more accurate prediction results. So this is one kind of a classification. So we can classify these the time series forecasting into some classical models, uh, the autoregressive integrated moving average, ARIMA models, exponential smoothing, and some advanced models like machine learning and deep learning. And like nowadays, people are much more studying the recurrent neural network, long short-term memory network, GRU network, CNN, amalgamation of these deep learning models. And there are the nowadays the research is much more focused on these advanced models. So there's an important term here in that we call it stationary. So stationary means that these statistical features of a time series are like mean, variance, and covariance. They do not change over time. So for example, if you look at the plot one, here the means varies, increases with time, and the result is like upward trend. Here you can see the trend is upward. And if you look at the second plot, there is no trend in the series. Somewhat is upward trend, somewhere is a downward trend, and this variance is vary over the time. And if you look at the third plot, in the spread becomes like closer in time series, like here in this particular area. So which means that the covariance is varying over time. Now why this is happening, like sometimes the model parameters, they have become very difficult to estimate, and the model becomes very less reliable. So stationary data with something with constant means and variance make it easier to estimate model parameters and and make more much more accurate prediction. So you have to allow, if you want to go for a more accurate modeling, you have to study the relationship between the past and the future observations. Otherwise you are not having any specific trend. So if you see this another graph, in this graph, like all three parameters are constant with time. Somewhere here, the stationary time series looks like. So it may happen when you have much more volatile workloads, where the workloads are increasing, decrease very rapidly. So to solve these kinds of problem, we much more goes towards this AI intelligence. So something which is much more related to algorithms that try to mimic the brain, the deep learning, machine learning, or AI, these buzzwords. And with the AI, then the artificial neural network, it is basically involved with the assembly of interconnected nodes and the weighted links. So we have these input nodes, and some weights are associated. We are summing these weights, and then based on the summation, we are comparing the output node against some threshold. So this is much more involved, like how accurately you are predicting these weights. So this is something which is much more black box. So we are applying LST and we are applying these deep learning models without studying like what is happening internally, so that we call the black box. And if you talk about more advanced neural network models, like something like this, where much more hidden layers are involved, and between input output you have like 3 layers, 4 layers, or more than that. So there are the different kinds of benefits of applying these kinds of models. So if you have like So it's not like deep learning, it's more about the data. So if you have like a large and complex data set, you think much more about these deep learning techniques, because you have to ensure, you have to capture like the complex dependencies between the multiple varies in the time. You always worry about improving the accuracy. So these kinds of model are very much useful when you have very complex patterns like the volatile workload pattern in the cloud and AI systems. And you have to continuously adopt to the new data. And apart from that, there are lots of dependencies, like you have to capture the temporal dependencies. So we'll be discussing with RNN and LSTM. You have to handle the long-term dependencies. And also like there's a popular buzzword, popular problem, technical problem, which we call the vanishing gradient problem. And so we'll start with some simple case study like the feed forward neural network. So this is one of the example, and we called a special name, which we call the feed forward neural network, because if you see, like, we have three layers: input layer, hidden layer, and output layer. And this is we call like feed forward, because every output in this layer, it depends on the input from the another layer. And you always the sequence will go in one direction to another direction, so we call it a feed forward. And this is one popular study for like image classification or the classification related problem. But whenever the caution comes of the time component, it is not that great, and due to which we need some special kind of neural network, that is we call like recurrent neural network, or RNNs. They are very important variant of neural networks. So generally, like the sequence forecasting models, they are evolved to better handling the time-based patterns. And initially, we have these RNN-based model or recurrent neural network models, because they can handle the sequential patterns of the data. But again, if you go about the problem, so their performance is often suffer due to major drawback, which is like they don't have a memory, a declining memory of previous data. So for example, like if you're reading a long book, and by the end you are struggling to remember what are the important details from the beginning. So this problem is we call the problem of like vanishing and exploding gradient issues. Like sometimes your gradient is become too slow, it becomes zero, and sometimes the gradient is exploded, and your model is not able to adapt to the behavior of data. Uh, so this is much more about related to the difficulty. So something like, for example, if you are using some old or previous video frames, and then you can might be well informed with the understanding of the present frame. So RNN can't do these things extremely. And for example, like consider a language model which is trying to predict the next word based on the previous one. So if you are trying to predict the word, let's say there's a sentence called "the clouds are in the sky," and apart from that, we are going to use the study "the clouds are," and then we are going to predict that okay, the next term will be sky. So it's pretty obvious. So where the gap between the relevant information and place that is needed is small, so RNN can learn use the past information. But we have when we have something like this, like here in the second layer, you can say there we have x1, and again there here we have h3 for the whole layer. So the things which we are using, when you have more context, more data, so it's very difficult, like it is entirely impossible to grab the information. So when the gap grows, like here in this picture you can see the gap is growing. So when the gap grows, it's very difficult to train, difficult to predict something. And the RNNs are become unable to learn and to connect these kinds of information. So that's why when you face this kind of problem, this is we called as the long-term dependencies. because it means that if you are predicting some data and the feature, the characteristics of data is much more depending upon the past long traces. So RNN don't seem to be able to learn them, and this is the fundamental reasons why it might be difficult. So LSTMs are there, which is called long short-term memory networks, which solves the problem. They add this memory element, and it's a special kind of RNN. And when you have uh, uh, you want to capture these extended patterns or the extended sequences, the LSTMs has introduced the studies. So they basically minimize the information losses over the long sequences. But again, the LSTMs are like still fall short in accurately predicting the volatile workloads in cloud edge environment, because although they are a special version of RNN, but if you are using like remembering like long periods of time, and when the workload is like highly volatile, they are not pretty much accurate. So that's why we move forward with the attention mechanism. So what is the meaning of attention? So basically the attention mechanism, this says that you are trying to improve the performance of deep learning models by focusing on the important input element. Now, what is the meaning of that? So, for example, if you look at the picture here, you can see like if I ask you by looking at the photo, like who is the teacher in the photo? So our brain, like it knows like what exactly what it has to do. So it will simply start looking for the features of an adult in the photo. So it treat like teacher as an adult in this photo, and the remaining features will be ignored. And this is which we call the attention. So our brain is very much adapting to the implementation. So the attention mechanism, they basically prioritize and emphasize on the related information, and then they enhance the model performance. So attention is very cognitive process in our mind. So that's why we can figure out like, for example, who's the teacher in this picture. So by considering this relationship, you are giving like much more weightage to the relevance or the important different data points. You're basically removing the distance in the sequence. So the attention mechanism, they can detect complex patterns, they can detect the dependencies that might be missed by other model. And this neural network is considered to be like effort to like mimic the human brain actions in much more simplified way. So attention, we can say that is an attempt to implement the same action of selecting or concentrating on a few relevant things while ignoring others in deep neural network. So you're finding which are the important weights, and you are discarding the useless weights which is there in your in the model. So nowadays, like people are much more focused about the hybrid kind of model, the hybrid LSTM attention models. Like here, you can see that it's basically adding the layers of CNN, RNN, and then you have attention layer. So this is we call like the hybridization of a model. And here comes the formation of the transformer architecture, which majorly relies on the attention mechanism to measure the relative importance of all input data points, which are the much more important data points. And the key advantage of transformer is like it provides like parallel processing of the input sequences. Like most of the approach which we have seen earlier, they have like sequential approach like in RNN or an LSTM. And so indirectly they are trying to boost the computational efficiency in this way. And there exists a complexity like uh, there could be different kinds of trends. So we have to basically remember those data points which are much more crucial, much more important to predict the upcoming time series. And they're basically handling the issues of attention. So this is like a picture. So it is one which is a little complex architecture to understand, but just for understanding, like you can remember three things. One is called the positional encoding, attention, and self-attention. So positional encoding in your time series, it means like the transformer will assign some positions or some index number that it can learn them better and remember them better. And attention is based on your inputs, like how much is the output will be generated, and that kind of relevant output and relevant working, that we call the attention. And self attention means, yeah, sometimes below between the lines you should be required to read, like take a reason for some intent. You have to understand some sentences. So that is we call like self attention. You're forecasting based on, suppose, something which is like external part. So there's a involvement of encoder and decoder. Now the thing is, like between the behind the transformer is like they are very advantageous. So there are different kinds of benefits. Like some of the benefits are listed, like they can handle better the long-term dependencies. So the trends, like from attentions, the researchers are much more focusing on the transformers in the time series forecasting, uh, because it can incorporate all kinds of external factors. And apart from these transformers, there's one more architecture which we call like n beats. So n beats, the full form is a little bit complex, like neural basis expansion analysis for interpretable time series forecasting. So it's basically the deep learning architecture that recreates the mechanisms of a statistical model using double residual stacks of fully connected layers. So I mean, it was basically used for the time series. And this is one of the interesting model, because as it's basically developed by Element AI, and they say that it is first pure deep learning model that outperform all kinds of existing models. So now when you study these kinds of models, like beginning from RNN, LSTM, attention, transformers, and beats, these models are really helpful in uh, something which is much more related to workload forecasting in cloud data centers. So this is one small example. So if you consider a single cloud data center which is having like lots of virtual machines, then you have physical machines. You are deploying these virtual machines to physical machines based on the capacity. And there's a resource manager. It could be like a cloud service provider, and it basically observing the behavior of these physical machines. It's recording what are their current CPU utilization, the memory utilization, and every information is gathered by this resource manager. And it is storing this workload. All these past workload traces all are stored uh, in this database. And there comes the role of prediction model. It takes all of this historical information and it forecasts like what will be the workload in the next time step. So this is very much important, because if you compare two decision making, like reactive and proactive, then there will be like significant gap in the performance. So for example, if we talk about the consolidation strategy, so this is one example here in this figure. So you can see, like this is one case A where two physical machines are there and some virtual machines are deployed. And this is like current utilization of these machines. Like it says like VM1, the current utilization of VM1 is 30%, current utilization of VM2 is 25%, and same with the VM3 which is deployed on physical machine 2, and it says that the current utilization of VM3 is 40%. And this number 55%, it belongs to the total utilization of PM1 at current time step. And this 40%, it says about the current utilization of physical machine 2, or the cloud server which is there in the cloud. And you if you're much more focused about the energy, so what you will do, you will just migrate this VM3 to physical machine 1, and you will just make your PM2 in sleep mode and you are trying to save the energy. Now here in time step t plus 1, you will see that the current utilization of VM3 is increased from 25% to 40%, and the total utilization is violating the upper threshold of this physical machine one. It's become more than 100%. So this is an example of service level agreement or SLA violation. Now here the prediction and the predictive model and forecasting models are quite important and relevant. So your model has to be more accurate, because if the forecasting was accurate, then you haven't migrated this VM3 to physical machine 1, and it may remain here and there will be no SLA violation. So there's a trade-off in energy and performance. So to maintain this trade-off, we need these kinds of deep learning models. So this one, there are lots of workload traces are there. Like if you want to go for some univariate time series for forecasting, Planet Lab is quite popular. Nowadays, Google cluster traces are launched. Like I recall, like in 2011, uh, when I was uh, when I was using this Google cluster traces. So the architecture was something like that. They have more than like 12,000 machines in 2011, and they have implemented, they have created a data set, and which is having different kinds of features, like with respect to CPU, memory, VM, uh, maximum memory uses, disk IO, and so on. And nowadays, like I guess like 2019, also Google cluster, they have updated workload traces, and the other traces are there, like CMAPS is there, and uh, we use these traces for study the behavior of a workload. And like in this Google cluster traces in 2011, they have like almost 20 columns, and I guess we have selected like 12 or 13 here, because we feel like these are the much more important in terms of training the model. So there are different things, like there could be like a start time, end time. So maybe we can skip or discard these, and then we can assemble like this cluster. The result of these clusters, they are basically collected for over like 10 seconds. And uh, like for our study, we have basically merged like for 5 minutes worth of data, and we have used like 10 days data, like 8 days for training the data and 2 days for testing the behavior. So this is one like data analysis. Now here you can see like how volatile these data sets are there. So this is only for one dimension for CPU analysis of Google cluster traces. These are like number of samples. Now here if you look at the picture, this is highly volatile and it has to be. Now if you want to go back with our study, like level, trend, seasonality, and noise, then these all are the important characteristics if you want to predict the behavior of a workload. And we can do like lots of data analysis. You can try to predict this behavior. Like here, if you find out their mean and deviation, then it will look something like this, like here. So we are quite far away from the actual uses. So this is something like rolling mean and standard deviation. And uh, to to study this behavior, what we have used, like to study the impact of this volatile workloads and behavior. Initially, we have started with the LSTM models, the bi-LSTM models, bidirectional, which can predict the behavior in both forward and backward directions. Then we have studied with attention layer, some with like hybrid model like this, where we have multiplicative LSTMs. So there are lot more versions of LSTMs are there, like vanilla LSTM. You can have the stacked LSTM or multiplicative LSTM. You can add attention layer, and then you can make some kind of hybrid architecture. So it's up to you, like what kind of workload you are using, and how do you utilize your yeah, model. And so for this kind of model, we have done lots of studies. Like here, you can see we have used the number of time steps. This is we call a popular term, which is multi-step ahead prediction. So where we have like a sequence of values in a time series. This is a very typical approach, and then we apply a predictive model step by step, and we use the predicted or forecasted value of current time for the current time step to determine like what will be the value in the next time step. For example, you are if we use this 90 steps ahead prediction, it means that mm for example, if you are reading a value of the variable for like last 90 hours, then you say that in future of 90 hours, what will be the current and past observation. So 90 steps ahead prediction means based on the actual value, the the behavior which you have studied, you are predicting like what will be the workload in the next 90 hours. So you can find out like uh, the CNN is really worst. Like this is basically used for the image processing stuffs, and the LSTM GRU is also one popular variant which we call the gated recurrent unit. And here these are having a similar behaviors. And uh, made if you build an integration of the models, if you had an attention layer or some stacked kind of model, then maybe your performance could be improved. And this is just like a prediction of different results. So in this study, basically we are taking all the features which are there in the Google cluster traces, and based on the number of time steps, we are predicting the CPU uses. Now sometimes what happen, like you have a problem of underfit and overfit, so it is like how much data you are using for a study. So these are different kinds of visualization behaviors for specifically on CPU uses, because our study is much more involved about the energy consumption. So that's why we have taken like the multivariate, but based on those behavior, we are predicting like what will be the CPU utilization. You can use other models like NBeats. Like here, we have NBeats model, and you can but the problem with this NBits is like you are using like you using this study for univariate workload prediction. And for example, only you are studying the time steps of CPU uses, and then you are predicting something, you're forecasting the workload behavior at the next time step. So this is basically involved with the cloud data centers, like the Google clusters workloads and these things. But if you look at much more bigger picture, like something which is involving all kinds of cloud and edge systems, something which we have seen initially with the continuum, uh, like this. So for this we need like like this model. So this is much more like high level design. Here you can say you have end users, the users may be on different locations. You have a workload manager, which is handling the workload, which is classifying the workload. And then you have like a continuum infrastructure, which is having all kinds of cloud data centers, edge devices. And you have different kinds of like energy provider policies and metrics which are involved. So we have taken a couple of use cases, like if you have energy sources, you have storage devices, energy prices, if you have energy policies, then how do you handle all kinds of research challenges of continuum. So and this is quite popular, like the we have added a new component which we call like grid control policies and regulations. Because nowadays what is happening, like to reduce the carbon footprint, we have an agency which we call like environmental protection agencies, EPA, which basically fine and punish the data center based on the carbon emission. And recently, like in the news, like Microsoft is partnered with the Swedish company called Vattenfall, and they basically provide solutions for data centers. So they are trying to build and deliver a like large scale 24 by 7 renewable energy matching solution. So for example, every megawatt hour of energy consumed in the data center, that has to be matched or mapped with the megawatt hour of renewable energy generation. So you're basically matching the energy consumption of a data center with the actual uses of renewable energy. Now, this is very quite and complicated, difficult and quite complicated task, and because it involves like how much energy is generated, how much energy is available, and so basically we have divided into different layers, and where like this is for end users, what kind of users are involved, what are their service types and service level. The workload is basically categorizing the types of incoming workload and selecting the hosting frameworks. Then we have different kinds of manager, like layer manager, where you have like single layer cloud systems or multi-layer cloud systems. And then we have like service managers, which is basically managing all kinds of gateways, frameworks, producers. The network managers, which is managing the establishing the communication rules. Then we have something which is called the workflow managers, which is managing or handling the dependencies and the life cycles of the workflows. And the important part is like integrating energy consideration. Now, here the AI is quite important, because we need something which can control all of these layers, which can uh, which can study the behaviors of these layers, behavior of workload, behavior of the cloud edge devices, and then it can use this study to make some more robust decision. So basically, you need a controller, and this is what you can have, where you have like sensors, and the sensors are basically uh, kind of a hardware attached devices. They are collecting data from various levels, and then you have like actuators or effectors, and these devices are basically used to enable or disable services through API calls, and then they are applied here. And here comes the role of which we call like the controller. So with this AI driven workload forecasting, we are basically studying the behavior of cloud edge computing. And there's one more similar kind of a project is going on in Europe, which we call like sovereign edge dot cognite project. So basically we are here they are trying to create like open source for Europe's next generation edge cloud. They are creating like edge cloud stacks for digital decades, and the framework is like the serverless and lots of. So basically, they will provide open source reference implementation of serverless continuum computing, and they are providing like a virtual and physical test bed which you can access around the globe. Lots of organizers are involved here, and the different use cases of the cognate, like you can use this for like smart cities, wi-fi detection, energy and cyber security. And so basically they will design a use case which is focused on securing the development and the operation of serverless workflows, and produce some smart mobility solution at the edge, and mm, a kind of a pipeline that will be implementing, integrating all kind of development and operations. So this is about like the test bed, uh, which is there in the which is implemented with the help of the northern Sweden at Rise, and it's basically a popular commercial and research data center. So they are basically developing and building like 2000 node container facilities across here. So this is which we call like uh, a cognitive test bed. And so the idea is like to create a, a serverless aware cloud edge continuum which can have all of these functionalities. So mm, that is from my side. And if you have any query, anything you want to ask, then please go ahead. So if you want to collaborate or incorporate like new technologies, then this is my mail ID, and uh, feel free to answer your queries. If you have any questions or anything you want to ask, then please go ahead.
Any queries?
Okay, I think so. I have some more time, so I could share some more important things here. Mm, okay. Okay. So if you're interested to work with some more like the time series based prediction, the workload forecasting. So the cluster data, like it was initially published in 2011, and but nowadays people are much more using this cluster which is on published on 2019. So um, so this is like version 3, and it provides like much more data which is on so this initially it was on like 12,500 machine in the Borg cluster. So there 8 Borg machines are involved. So you can study the behavior of the data, which much more variety and much more use cases are involved. And also like there's one more data traces that we have, which we call like uh, Planet Lab. I'll check whether it's available here or not. Okay, I don't think it's there. Okay, so okay, yeah. So this is there like if you are interested in much more like if you want to interested the data driven challenges, then you can uh, go with this warehouse like so here this is basically funded by the Wellenberg AI Autonomous Systems and Software Program, and you can find out much more scalable data set here. And yeah, so much more people are involved here. And this is the basically the portal of FeraOps. And it basically provides the data access to all researchers. You can browse the data, you can process it in a integrated and GPU accelerated compute platforms. You can request the CPU and GPU resources. You can host your data, and they have more than like data which you can imagine. Like uh, this is something much more related to data which is in terabytes. So you have to study these in batches. So this is a much more popular platform. So if you want to study some data which is related to the telecommunication or something which is related to energy, then this is one popular forum. And other one which we have discussed, which is on energy, that we call the electricity maps, that is also quite popular. So if you want to study the green energy uses, and if you want to predict something which is like how much energy will be required, so that is another kind of data that you can use in your study. Okay. Anything